Okay, so that's the example. Hopefully that's helpful. Let's try to look at some of the more abstract things again. Let's look at this spectrum. Right? I already mentioned that pretty much everything is set associative cache. Right? The direct map cache is an extreme case. This fully associative cache is also extreme case. One thing is, right, given the k-way, right, given the k-way block, k-way cache with n blocks, the first thing you guys want to do is to determine the number of sets. Okay, how many sets do we have? We just do n over k. Right? Then you can directly determine. Right, you just take the log, and then you can directly determine the number of index bits that we need. For fully associated cache, that's the extreme case. So that's where k is the same with n. Right? Basically, we have an n way. We have n blocks, and then we have an n way associated cache. So that's where we only have one cache set, right? One set, which means really zero index bits. Right? For direct map cache, k is 1, just one way. Then we have n cache sets. Okay. In general, increasing the associativity usually helps. Usually helps us improve the hit rate or reduce the miss rate, right? But again, there's a trade-off, right? If you think about the extreme case, the fully associated cache, we have to search all the ways in parallel at the same time. You can imagine that if n, right, the number of ways is large, we will need to build a very large, very complex combinational logic, right? We have many comparators, and then all of those need to go to an OR gate, right? So that OR gate may have many inputs. We may increase the clock cycle time, right, and reduce the clock frequency. So that's one downside. Of course, also the area, right, and the cost, the power. So that also goes up pretty quickly. So that's where we always need to make the trade-off. Okay, so let's try to be, we just talk about this abstract notion of a spectrum. Right? Let's try to be more concrete. Let's try to practice the address breakdown again. Here's the spectrum, right? We have direct map cache, right? Set associative cache, two-way, four-way, and fully associative cache. So here I assume that I have 8 blocks in the cache, 4 bytes per block, and the total bits, right, in the memory address, in the full memory address is 16. So first, the easy question, right, the easy thing, byte offset, how many bits? How many bits for byte offset? 2 bits. Very good. We have 16-bit, right, full memory address. What does that mean? Means that since first the byte offset that is 2-bit, right, means that tag plus index is 14 bits, right? Makes sense, right? The rest, basically tag plus index, 14 bits. What is this thing again? There's a name for, if you combine these two, there's a name for this address, right? What is this name again? Tag plus index. This is not a full memory address. What is this address? Very good, Stephen. Memory block address. Okay, keep this in mind, right? And when you read the homework question, when you read the exam question, make sure that you distinguish memory block address from memory address, full memory address. There's this difference, right? The subtle difference. Okay, so this is right. This is fine, right? So let's look at each individual case. First, one way, right, or direct map cache. We have 8 blocks. How many index bits do we have? Direct map cache, 8 blocks. And how many tags do we have? 3 for index, right? Since we have 8 blocks, 2 to 3 is 8. And the rest, right? So 3, we have 14 bits for tag plus index. So the rest is 11, right? Okay. Next one. Any guess? Do we have? Let's just go through the exercise first. Index, how many? We have 4 sets now, 2-way, right? 2 blocks per 2 ways per set. And we have 4 sets, 2 bits. Tag. How many bits for tag? 12. Okay, again, 2 plus, right? 12 is 14. All right, next one. Any guess? Hopefully the trend is already clear. So with this spectrum, if you increase the number of ways, do we have more tag bits or less? We have more tag bits, right? In this case, we have 2 sets, index just in 1 bit, tag 13. Okay. Last one, fully associative. Tag, we don't even care for index, right? Index is 0. Tag is 14. Okay. What does this mean? Really, you look at the tag, right? You want to understand how much flexibility do you have for the cache, the memory to cache mapping. All you need to look at is the tag, right? If you have more tag bits, that means you have more flexibility, which makes intuitive sense, right? Okay. In case this is still not too intuitive, let me ask you guys one more question. Let's come back to this configuration again, direct map cache. Let me ask you, so in this case, okay, I talk about direct map cache, it's a many-to-one mapping. So we are mapping many different memory block addresses to the same cache location, to a single cache location, right? So what exactly is, how many are we exactly mapping to the single cache location in this case? How many distinct memory block addresses are we mapping to one cache block or one cache location with this direct map cache? Can you directly tell me based on the information that we have derived so far? How many? I think about, we have, right, in the analogy, right, we have 8 phones, right, with direct map cache, but 2 pockets, right, it's a 4-to-1, right? If you have, right, so 4 pockets is 2-to-1, right? But in this case, can you just directly tell me, based on the information that we have derived, what is how many to 1? How many memory blocks are mapped to the same cache location? Any guesses? It's actually very good, Stephen. 2 to the 11, which is, right, all you guys need to care for is the tag bits. Right? That's basically tells you how many different choices you may have, right, in that corresponding cache block or cache set, right? This tells you how many different variations you may have. Okay, Ash is asking, are all of this roughly the same speed? A very good question, actually, right? Again, there's a trade-off, right? By speed, I guess you're referring to the delay, maybe, right? With fully associated cache, it's gonna be more expensive in terms of the delay, right? In terms of the critical path, because we do need to search all these ways in parallel. So basically, there's a trade-off. They do not have the same speed, but we have to balance it. We are going to talk more about this in the next lecture. So there's the trade-off. In certain cases, right, this overhead may be just too much. Right? We're paying too much overhead to increase the hit rate. That may not be even worth it. So that's where we actually need to run a lot of empirical experiments just to determine what is the best configuration for our system. Does that make sense? Right? They are not the same in terms of speed. Direct map cache is faster to access. You just need to extract the index bits, right? And then do a single comparison. Okay, And also, there's another way, right? There's another more systematic way to analyze the performance of different kind of caches. So we can first actually break down the different kind of misses into 3 categories, 3 classes. The first one is called a compulsory miss. Usually we just call it a cold miss. With a cold miss means that we haven't seen this memory block address before. This is really the first access to this specific memory block. That's where, regardless, right? Regardless of what we have in the cache, it's going to be missed, right? Because we haven't seen it yet. We haven't accessed this memory block yet. That's why it's called a compulsory miss or cold miss. Means the cache is still not warmed up yet, right? Still cold. Second one is called capacitive miss. So this is where we say that the cache is just not large enough, right? Because ideally, we talk about, again, also the intuition behind the cache, right? Main memory. So ideally, we really want a very, very large SRAM so we can hold all the data, right, that we want to access, but that's just too expensive. That's why we build a cache, right? So where we have a smaller SRAM that act as the cache, and we have a bigger main memory, which is implemented by DRAM, right? And these two work together to form the memory hierarchy. If the cache, but we do have a limitation, right? Since we have a limited size in the cache, capacity in the cache, in some cases we may have to miss because we run out of space. So that's so-called a capacitive miss. We also have something called complete miss. So this is where we have a miss because of the inflexibility of the block placement or the mapping. Right? We already talked about some of this, right? For direct map cache and some of the set associated cache, multiple memory addresses, memory block addresses are competing for the same cache set or same cache location. That in some cases cause the misses. That's called a complete miss. For direct map cache, this happens more often, right, than the set associated cache with more associativity. And in the extreme case, when we are looking at the fully associated cache, there's no complete miss because we don't have such restriction on the block placement. Okay, so this is still pretty abstract, right? But hopefully, at least the first one is very intuitive, right? The first one, the cold miss, is very intuitive. And I'm going to show you guys some example to help you distinguish complete miss from capacitive miss. There's actually some subtlety that involved. Let's look at a concrete example again. Here I'm using a table to show a direct map cache. Right. So first, I'm giving you a address scheme, address sequence. This is an address stream. Over here, I'm using the block address. Okay, this is the memory block address. I have 5 addresses to access, and these are all in decimal. Right. Okay, so first, this is a direct map cache. The assumption here, we have 4 blocks. Okay, 4 blocks. 0, 1, 2, 3. Direct map cache. Later, I'm also going to show you guys the scenario with set associative and fully associated cache. All right, first one, direct map cache. How many index bits do we have in this case? One more time, 4 blocks, direct map cache. We don't care for the byte offset, right? Since we are directly looking at the block address. 2, right? Very good, 2. So if we translate it, we also use the decimal index, right, for the cache blocks. For the first block address, right, see here, this is all 0, right? Obviously the cache, right, the corresponding index, right, it's also 0, it's all 0, right? Regardless how many bits do you have for index bit, this can be we're going to access cache block 0. 8. We have this a sequence. This is a time, right? So basically, we access 1 block address at a time, and the arrow points to the right. This indicates the time. What is the corresponding cache index for block address 8? In binary, this is 1000, right? We have 2 index bits. We take this 2, so this is still a 0, right? Okay, and this is also 0, right? How about this guy? 6. What is the cache index? This is 0, 1, 1, 0. Okay, this is a 2, right? This is a 2. Last one, 8 is also 0. All right, hopefully this is clear. Okay, we already translated the memory block address into the cache, right, block address. All right, so with this in mind, first one, do we have a hit or miss, right? Initially, all the cache, right? The cache is sort of invalidated, no valid entry in the cache. So we haven't seen the, right, this block address before. This is a miss, right? What kind of miss? Co-miss, conflict miss, co-miss, right? Very good. This is a co-miss. And we put the corresponding data block right over here in the cache. Second one, is it a hit or miss? 8. Let me look at 8. It's also a miss, right? And it's also a co-miss since we haven't seen 8 before. Also a miss. And since we are also addressing cache block 0, so that's where we have to evict M0 and then replace it with M8, right? So this is where we have, right? So this is inflexibility. So we have to kick out M0. Again, the column, the rows, right? So this is this evolve over time. Next one, so we read 0 again. We read 0 again. Is it a miss? This is not a co-miss anymore, right? We have seen 0 before. It cannot be a co-miss. But this is still a miss. What kind of miss do we have? Any guess? This is conflict miss. Very good. Right, this is actually a conflict miss. I'm gonna make it a lot more concrete. So when do we have conflict? When do we have a capacitance later on? Most likely in the next lecture. Okay. We put M0 back, right? We kick out M8. Next one, 6, also miss, right? We put M6 here since we are addressing block 2. Block 2. This is also a miss. What kind of miss? Co-miss. Very good. Last one, 8. 8 again. Okay. We still have M0 here, right? At this point in this time. So this is also a miss, right? Unfortunately, still a miss. And is this a co-miss? This one. No, right? We have seen 8 before. So this is a conflict miss. All right. Any questions? Here's what I just worked out. Over here, I'm using the color code to make it more clear. Blue miss like this. Blue miss means a co-miss. A red miss like this means a conflict miss. So this is my color code. Right. This is direct map cache. Let's quickly look at two-way set associative cache. So now we have 2 ways, right? 4 blocks. We still have 4 cache blocks. 4 blocks. So we have 2 sets, right? 4 over 2, which is 2 sets. 4 blocks, 2 ways, 2 sets. Right? So that's that. What is the cache index values? Also, this is time, right? We are looking at this. Right? This is the time. This is the direction of time. How many bits do we have for cache index? How many bits? We have 2 sets. Just one. 2? Is it 2? 2 bits? Just 1, right? 1 bit. Okay, because we just have 2 sets. Okay, we are addressing the cache sets. All right, so this is going to be 0, right? Cache index so it's 0 and 8. 8 again is 1 0 0 0. We take the last bit, right? 0 0 again 6 0 1 1 0. Also last bit is also 0, right? And 8 0 again. Is it clear? So this is my cache index. So first one, same thing, co-miss, right? Okay, there's a co-miss. We put M0 here. Second one, when we access 8, this is also a co-miss, right? But we do not, so since we have a 2-way, right, set, we don't have to remove M0. we put M8 here. Next one, do we have a hit or miss? Very good. So this one is a hit, right? Because M0 is here and M8 is still here. This one, 6. We also, right, because of this is still two-way, right? This is not fully associated. So we still have some inflexibility in terms of the cache block placement. This one's going to be a cold miss, right? Since we haven't seen 6 before, but we have to evict, right? We have to remove one of the blocks from the cache set 0. So let's say we remove the one that's not accessed most recently. So we remove this guy. M6, put M6 here. M0 remains in the set 0. Okay, let's do this. Then, unfortunately, this is just not a great decision, but this actually happens, right? Quite often, unfortunately. When we access 8 again, this is a miss, right? Since we just evicted, we just move out, kicked out 8. So we have another miss. Is it a cold miss? What kind of miss are we dealing with? Is it a capacitor miss? It's actually a conflict miss. We are going to talk about, right? Why is it a conflict miss? But this is actually a conflict miss. Then we replace M0 with M8. Okay. All right, any questions so far? And these are my cache organization, right? 2 ways per set. Right, this is what we just went through. We have some, right? We do have a hit in this case, right? And we have a conflict miss. We still have a conflict miss because of the restriction of the two-way, right? It's not like fully associative. We do have some restriction. We can only place all of this, right? 0, 8, 6, all to the same set 0. All right, so this is not something that I'm gonna, right? For fully associative cache, right? This is actually fairly straightforward, right? I'm not gonna go over each row one at a time, but let's just quickly look at this, right? First, this is a cold miss, right? Since it's a fully associative, we basically have 4 ways, right? 4 blocks, full flexibility. We don't really need a cache index, 0 bits, right, for cache index. So any memory block can go to any way, which is the flexibility, right? First, we have a cold miss, right? There's a cold miss, and then we put M0 here, right? Next one, also cold miss, so we put M8 here. Okay. Next, we have a hit, right? Because M0 is here, which is nice. This is also cold miss, right? But instead of evicting either M0 or M8, we now have the flexibility of putting M6 in the third way, okay? Which turns out to be useful in this case, right? Because when we access 8 again, we have a hit, right? Because 8 was not evicted by M6. That's where fully associated cache becomes useful. Okay, any questions? If not, let's quickly talk about the block replacement policy. Right, at a certain point, when we look at this direct map cache and also set associated cache, right, we have to remove, right? We have to evict certain block when there's a conflict in terms of the mapping, right? In terms of the block placement. For direct map cache, really, there's no choice, because if there's a conflict, right, we have to evict the existing block from the cache. No choice. But for set associated cache, we do have some choices, right? Including fully associated cache. So which way do we pick? There are multiple ways. In case all the ways are already occupied, they're all valid, they're all occupied, we have to evict a certain block from one of the ways. One of the common policies that we use is the so-called LRU, least recently used policy. Okay. The meaning of LRU is that when we have to make a choice, when we have to remove one of the cache blocks from one of the ways, we choose the one that's the oldest, the one that's the unused for the longest time. That's why it's called least recently used. Why do we do this? Any guess? Why do we do this? Why is this a good idea in most cases, or in the majority of cases? Why is this a good idea? Why do we evict the ones that's not recently used? There are two things, right? We talk about locality. Then we talk about, right, the cache, right? Cache makes sense. Cache works because of locality, data locality, right? Right, very good, Stephen. And there's something called temporal locality, meaning that if certain block is accessed recently, most likely it's going to be accessed again, right, in the near future. That's so-called a temporal locality. That's why we like to keep the most recently used cache block in the cache. And also there's something called spatial locality, right? So that's why we load the entire cache block, right? Not just a single byte or a single word. Okay, of course, there is some overhead, right? If we are doing this kind of LRU scheme, we have to keep the age, right? We need to know the age, how old is a cache block. That's where we need additional storage, we need additional logic. Usually, if we go above 4 ways, so this kind of overhead becomes pretty large. Right? And if we indeed have to go to cache, use a cache with a higher associativity, with more ways, in many cases, we just select randomly. We just choose one arbitrarily. That's cheap enough. Okay. All right, so this is to help you guys understand what exactly does LRU mean. This is another example. This is also the last slide for this lecture. Over here, we have a longer address stream. Okay. Again, this is the time. We are accessing the memory blocks. We are dealing with a fully associative cache here, so no cache index, which is right, nice, right? This is flexible. Okay, if you look at the sequence here, right, we have quite a few code misses. Right? So these are the code misses because we haven't seen this memory block address before. But one tweak that we have, this is one new thing. We are adding this H bits, see here, in the parentheses. This is so-called LRUH. We have 4 ways, right? This is a fully associative cache. We have 4 blocks, right? We have 4 ways. That means, you know, we have 2 bits, right? We need to keep track of the relative age for each block. So in this case, we allocate 2 bits, right? First, if you look at the first row, row 0, we access M0, right? That's where we have a newborn, right? Sort of, right? This is where we access the new address, new block address. We set the age, right? This is real age to be 0. This is a newborn. And next cycle, or maybe next, right? Not necessarily next cycle or the next slot, time slot, when we access this main memory again, when we update the cache, so we update the age, we increment the age from 0 to 1 for this specific cache block. Okay. Same thing over here, right? You look at M4, when we first access it, we set its age to be 0. And then we increase the age per cycle or per access. All right. So at a certain point, so that's where we have to make a eviction. So in this case, we have seen this, right? We have seen this 0 before, block 0, address 0 before. So this is not a comiss, and this is actually a capacitor miss in this case. I'm gonna explain why this is a capacitor miss in the next lecture, not a conflict miss. Okay, but since by definition, right, since we are dealing with a fully associated cache, there's really no conflict miss by definition for associated cache, fully associated cache. There's no conflict miss. So that's why we have a capacitor miss. And see here, we put M0 here. We evict M4 because M4 has the oldest age. M4 is least recently used. Anytime we access a block address, we reset SH to 0, like this. We reset M0 to have an age of 0 because it's the most recently accessed. Is it clear? So how does LRU works? Right. Hopefully it's going to be somewhat intuitive, right? So this indeed incurs additional overhead, right? Basically, per cache block, we need to maintain certain age information, and we also need to make a comparison, right? We need to find which block is the oldest one. Although it sounds cool and cold-blooded, right? We are evicting the oldest guy, right, in the cache. But unfortunately, right, so based on the principle of the temporal locality, this seems to be in fact effective. This seems to work in many cases. Okay, and next lecture, we are going to be analyzing, right, how we distinguish a capacitor miss from a conflict miss. So I'm going to give you guys a much more concrete way to make that analysis. All right. So like I said, this is my last slide, right? If you guys have any question on